Hello viewers, welcome to today's section of food technology under which you will be studying about lipids. In continuation with the first part, let us learn about the physical and chemical properties of lipid in this unit. In earlier unit, you learnt about the definition of lipids followed by classification. You also learned how lipids are named based on their common name, systemic name or Geneva name and omega system. Lipid plays an important role in foods. In addition to their nutritional importance, lipids are also used in foods because of their characteristic physico-chemical properties. They are used as heat transfer agents during the preparation of other foods. In order to make changes in lipid composition while ensuring the production of high quality foods, a fundamental understanding of the chemical and physical properties of lipids is critical. It is important to know analytical techniques that can be used to characterize the physico-chemical properties of lipids. Therefore, this chapter focuses on the chemical and physical properties of lipids. Through this study, you will be able to understand physical properties and chemical properties. Under physical properties, you will be studying about melting point, softening point, specific gravity, refractive index, smoke, flash and fire point and turbidity point. Under chemical properties, you will be studying about Richet-Missel value, Polanski value, iodine value, peroxide value and saponification value. Now, let us start with the physical properties. The first one under physical properties is melting point. When a pure chemical compound is heated, it undergoes a phase transition from solid to liquid at sharply defined temperature. The melting point is an index of force of attraction between molecules. The greater the attractive forces between molecules, the more easily they will associate to form a solid. It is harder to separate them when they are in the crystalline form and convert them to a liquid. A lot of energy in the form of heat must be put into convert a solid to a liquid. Therefore, melting point will be high for particular fat. In other words, a high melting point indicates a strong attractive force between molecules. A strong attractive forces indicates a good degree of fitness between the molecules. Molecules that do not fit together well do not have strong attractive forces holding them together. Therefore, they have a low melting points. A fat or oil which is a mixture of several triglycerides has a lower melting point and a broader melting range. The melting range is dependent on the fatty acids of the component triglycerides. Fats also may be plastic at room temperature containing some triglycerides that are liquid and some that are solid. Oils, liquids at room temperature tend to be more unsaturated, have shorter chains and have lower melting points. Fats which are plastic or solid with long chains and high melting points at room temperature. As mentioned, the melting point of a fat or oil is actually a range, not a sharply defined temperature. Each fat or oil contains triglycerides that melt at different temperatures depending on their component fatty acids. Some fatty acids have a wide melting range, whereas others such as butter or chocolate have a narrow melting range. Chocolate has a narrow melting range that is close to body temperature. This accounts for its characteristic melt in mouth property. The melting points of individual fatty acids depends on chain length, number of double bonds which is the degree of unsaturation and isomeric configuration. All these factors affect the degree of fit and the force of attraction between fatty acid molecules. The first one under this is chain length. Long chain fatty acids have a higher melting point than short chain fatty acids. Potential for attraction is more between long chains than there is between short chains. For example, butyric acid which has 4 carbon atoms has a melting point of minus 7.9 degrees Celsius, whereas stearic acid which has 18 carbon atoms has a higher melting point of 69.6 degree Celsius. Stearic acid is a crystalline solid and butyric is a liquid at room temperature. The second consideration is number of double bonds. As the number of double bonds increases, the melting point decreases. Double bonds introduce kinks into the chain and it is harder for molecules to fit together to form crystals. Therefore, the attractive forces between the molecules are weaker. This is demonstrated by comparing the melting points of stearic, oleic, linolenic and linolenic acids in the table. The next is isomeric configuration. Geometric isomers have different melting points. Cis double bond configuration introduce a much bigger kink into the molecule than does the trans configuration. Consequently, the cis isomer has a lower melting point than the trans isomer. Now, let us see how melting point is determined. Melting point is determined by open tube capillary slip method. The principle in this method is the temperature at which the oil or fat softens or becomes sufficiently fluid to slip or run as determined by the open tube capillary slip method. The procedure for estimation of melting point of fats is fat sample is melted and filtered. A capillary tube is introduced into the molten sample. Tube is chilled immediately until the fat solidifies. Tube is placed in a small beaker for 1 hour at 4 degrees Celsius to 10 degrees Celsius. Then the tube is removed and attached to a rubber band for the thermometer to the thermometer bulb. Water at 10 degrees Celsius is taken in the thiol tube and thermometer is immersed with the capillary tube containing fat sample. Gradually, temperature is increased by heating the thiol tube till the temperature reaches 25 degrees Celsius and thereafter at the rate of 0.5 degrees Celsius per minute. The temperature of the water when the sample columns begins to rise in the capillary tube is noted. Next physical property is softening point. Fats do not melt immediately but soften over a range of temperatures. This property is called softening point of fats and gives each fat its unique character. A plastic fat is moldable because it contains both liquid oil and solid crystals of triglycerides. If liquid triglycerides are more, fats will be softer. If solid triglycerides are more, fats will be harder. A plastic fat is a two-phase system containing solid fat crystals surrounded by liquid oil. The liquid phase acts as a lubricant enabling the solid crystals to slide past one another. Therefore, fat can be pressed and molded into shapes without breakage. A fat that contains only solid triglycerides is brittle and cannot be molded. In these, the crystals cannot move past each other. Now, let us see the determination of softening point. The principle for determination of softening point and melting point is same. In melting point estimation, open capillary tube is followed, whereas in estimation of softening point, closed capillary tube method is followed. The end point is the physical movement of the fat column under a standardized hydrostatic pressure. The third physical property is specific gravity. The term specific gravity is used to denote the ratio between the weight of a substance and the weight of an equal volume of water. The weights are compared at the same temperature. The specific gravity of fats is less than 1, which is about 0.86, and therefore they float on water surface. Solid fats are lighter than the liquid fats. Oils spread on water to form thin layers. The procedure for the estimation of specific gravity is using pycnometer. As you can see, the dry pycnometer is filled with the sample. Stopper has to be inserted and immersed in water bath at 30 degrees Celsius for 30 minutes. Carefully, it has to be wiped away any extra oil if it is coming out of the capillary opening. The bottle has to be removed from the water bath, clean and dry it thoroughly. The cap has to be removed and quickly weigh, ensuring the temperatures does not fall below 30 degrees Celsius. The specific gravity at 30 degrees Celsius by 30 degrees Celsius is A minus B divided by C minus B, where A is weight in gram of specific gravity bottle with oil at 30 degrees Celsius, B is weight in gram of specific gravity bottle at 30 degrees Celsius, and C is weight in gram of specific gravity bottle with water at 30 degrees Celsius. If the specific gravity of an oil is given as 0.919 at 25 by 25 degrees Celsius, it means that the weight of the oil at 25 degrees Celsius is compared with the weight of an equal volume of water at 25 degrees Celsius. The average specific gravity of some edible fats and oils are butter not less than 0.905 at 40 degrees Celsius, cottonseed oil 0.9172 to 0.918 at 25 degrees Celsius, corn oil 0.9192 to 0.921 at 25 degrees Celsius, lard 0.9312 to 932 at 15 degrees Celsius, and olive oil at 0.916 to 918. The next physical property is refractive index. Refractive index is the ratio of velocity of light in vacuum to the velocity of light in the oil or fat. It expresses the ratio between the sine of angle of incidence to the sign of angle of refraction when a ray of light of known wavelength passes from air into the oil or fat. Refractive index varies with temperature and wavelength. Measurement of refractive index of the sample is carried out by means of suitable refractometer. The procedure for measuring refractive index is: fat sample has to be melted and filtered, circulate stream of water through the instrument, the temperature has to be adjusted and the desired temperature has to be set. The prism should be clean and dry. A few drops of sample has to be put on prism. Prism has to be closed and allowed for standing for 1 to 2 minutes. The instrument has to be adjusted to obtain the light and direct distinct reading possible, and refractive index has to be determined. Next physical property is smoke point. The smoke point is the temperature at which fat gets heated before continuous puffs of blue smoke come from the surface of the fat under controlled conditions. The presence of smoke indicates that free glycerol has hydrolyzed to acrolein. Acrolein is a mucous membrane irritant. Monoglycerides in hydrogenated shortenings and diglycerides are hydrolyzed more easily than triglycerides. Monoglycerides and diglycerides tend to have a low smoke point. There are many factors which affect the smoking point, as you can see in the screen. Smoking point is measured by using the AOCS method, and the procedure is: oil has to be taken in a deep frying pan. The oil has to be heated on a low flame. The emission of smoke has to be noted down. The time taken and the temperature has to be noted down. Smoking temperature is important for fats used for frying. Fats with low smoke point are not suitable for frying because of the odor and irritating effect of the fumes. The decomposition products may give an unpleasant flavor to the food. Hence, it is preferable to use fats with relatively high smoking temperatures for frying. Next physical property is flash point. The flash point is the temperature at which the volatile products generated by the lipid are being produced at a rate where they can temporarily ignited by application of a flame but cannot sustain combustion. Flash point is determined by Penske-Martin method, and the method helps to determine the temperature at which the sample will flash when a test flame is applied. The procedure for estimation of flash point is: the sample is heated in a test cup at slow and constant rate with continual stirring. A small test flame is directed into the cup at regular intervals with simultaneous interruption of stirring. The flash point is taken at the lowest temperature at the test flame, causes the vapor above the sample to ignite momentarily. Next physical property is fire point. The fire point is the temperature at which the volatile products will support continued combustion with application of flame. Measurement of these temperatures are particularly important when selecting lipids that are going to be used at high temperatures, example during baking or frying. Next physical property is turbidity temperature. Oils containing long chain saturated fatty acids give a precipitate at a particular temperature. This temperature is specific for the oil when their alcoholic soap solution is treated with dilute acetic acid solution and 70% ethyl alcohol. Turbidity temperature is measured by using following Bellier test using acetic acid. The procedure for estimation is: 1 ml of oil is taken in a 100 ml conical flask to which 5 ml of 1.5 normal alcoholic potash is added. The sample has to be completely saponified by heating over a boiling water bath, and the flask has to be swirled several times. The flask has to be cooled and phenolphthalein indicator is added and neutralized with dilute acetic acid, to which 50 ml of 70% ethyl alcohol is added and mixed. A thermometer is fixed into the flask and immersed in the liquid. The flask is heated on a water bath till the temperature reaches 50 degrees Celsius. The flask is allowed to cool and the temperature at which the first distinct turbidity appears is noted down. Now, let us start with the chemical properties. The first one under chemical properties is Richet-Missel value and Polanski value. The Richet-Missel value is the number of milliliters of 0.1 normal aqueous sodium hydroxide solution required to neutralize steam volatile water soluble fatty acids distilled from 5 gram of an oil or fat under the prescribed conditions. It is a measure of water soluble steam volatile fatty acids, chiefly butyric and caproic acids present in oil or fat by the following method. 5 gram of sample is taken in 300 ml distill flask, to which 20 ml of glycerin and 2 ml of concentrated sodium hydroxide solution is added. It has to be heated over a flame until it completely saponify. Cool the contents and add 90 ml of distilled water, to which 0.6 to 0.7 gram of pumice stone grains is added, plus 50 ml of dilute sulfuric acid solution is also added. Immediately the flask is connected to the distillation apparatus. It is heated very gently until the fatty acids melt and get separated. This is collected in a graduated flask. About 110 ml of distillate is collected. Then the graduated flask is stoppered and it is placed in a water bath which is maintained at 15 degrees Celsius for 10 minutes. The graduated flask is removed from the cold water bath. Then the outside and the contents is mixed thoroughly. The content is filtered through Wattmann number 4 filter paper. Then 100 ml of filtrate is taken, to which 5 drops of phenolphthalein solution is added and titrated against 0.1 normal sodium hydroxide solution. A blank also has to be run without the addition of fat but using the same quantities of reagents. The calculation for Richet-Missel value is A minus B into N into 11, where A is volume in ml of standard sodium hydroxide solution required for the test, B is volume in ml in standard sodium hydroxide solution required for the blank, and N is normality of standard sodium hydroxide solution. Now next is the Polinske value. The Polinske value is the number of milliliters of 0.1 normal aqueous potassium hydroxide required to neutralize steam volatile water insoluble fatty acids distilled from 5 gram of fat or oil under the prescribed conditions. It is a measure of steam volatile and water insoluble fatty acids, chiefly caprylic, capric, lauric acids present in oil or fat by the following method. After collecting the soluble volatile acids by the Richet-Missel method, the condenser, the graduated flask and the filter paper has to be washed thoroughly with cold distilled water. The washing has to be discarded and then the insoluble contents has to be washed in the condenser, in the flask and the filter paper using ethyl alcohol by 3 times. All the alcoholic washings has to be collected in a clean flask. To this 5 drops of phenolphthalein indicator solution is added and titrated with standard sodium hydroxide solution. The Richet-Missel number measures the quantity of short chain fatty acids in the fat molecule. The Richet-Missel numbers of coconut and palm oils range between 5 and 8. Butterfat is exceptional in having a high Richet-Missel number ranging from 17 to 35. This high value makes possible the detection of any foreign fats which are sometimes adulterated in the manufacture of butter. Coconut and palm kernel oil contains appreciable quantities of caprylic and capric lauric acid glycerides. These fatty acids are steam volatile but not soluble in water and hence give high Polinske value. Next, chemical component analysis is iodine value. The iodine value is defined as the percentage of iodine absorbed by an oil or fat or wax. The iodine value is simple and a rapidly determined chemical constant for a fat or oil. It is a valuable characteristic in fat analysis that measures unsaturation but does not define the specific fatty acids. Iodine value analysis are very accurate and provide nearly theoretical values. Iodine value is a useful tool for process control and product specifications. Iodine value is a measure of the unsaturation of fats and oils and is expressed as the iodine absorbed per 100 parts by weight of fat. The following method is used to measure the iodine value of fat sample. The method for measuring iodine value is, the iodine value is measured by weighing approximate quantity of oil or fat in a 500 ml conical flask with the glass stopper to which 25 ml of carbon tetrachloride have been added. This contents has to be mixed well, to which 25 ml of Vigi's solution is added and the glass stopper is replaced. The content has to be swirled properly and the flask is kept in dark for half an hour. Carry out a blank simultaneously. After standing for half an hour, potassium iodide solution about 15 ml is added, followed by adding boiled and cooled water about 100 ml. The titration is carried out in which the liberated iodine is titrated with standardized sodium thiosulfate solution using starch as indicator at the end until the blue color formed disappears after through shaking. A blank has to be conducted to determine in the same manner as the test sample but without oil or fat. The calculation for estimation of iodine value is 12.69 into B minus S into N divided by W, in which B is volume in ml of standard sodium thiosulfate solution required for the blank, S is volume in ml of standard sodium thiosulfate solution required for the sample, N normality of standard sodium thiosulfate solution, and W is the weight of the fat sample in grams. The iodine value procedure must be performed very precisely and timed carefully. Oils like soya bean, corn and cotton seed have higher iodine numbers than the solid fats such as beef fat or tallow because they contain more unsaturated fatty acids in the fat molecules. The next chemical property is the peroxide value. Oxidation of lipids is a major cause of their deterioration. Hydroperoxide formed by the reaction between oxygen and the unsaturated fatty acids are the primary products of this reaction. Hydroperoxides have no flavor or odor but break down rapidly to form aldehydes which have a strong disagreeable flavor and odor. The peroxide concentration, usually expressed as peroxide value, is a measure of oxidation or rancidity in its early stages. Peroxide value measures the concentration of substance that oxidize potassium iodide to iodine in terms of milliequivalents of peroxide per 1000 grams of sample. Peroxide value is one of the most widely used chemical tests for the determination of fats and oils quality. Peroxide value shows good correlation with organoleptic flavor scores. The method to estimation of peroxide value is sample about 5 gram is taken in 250 ml conical flask to which mixture of acetic acid and chloroform is added and it is swirled to dissolve. For this 0.5 ml of saturated potassium iodide solution is added and it is let to stand for 30 minutes in dark with occasional shaking and 30 ml of water is added. 0.5 ml of starch solution is added and titrated against 0.1 normal sodium thiosulfate solution until the yellow color is almost gone. The calculation for estimation of peroxide value is titer multiplied by normality multiplied by 100 divided by weight of the sample, where titer is the ml of sodium thiosulfate used in blank, N is normality of sodium thiosulfate solution and peroxide value is expressed as milliequivalent of peroxide oxygen per kg sample. The next chemical property is saponification value. The saponification value is defined as the number of mg of potassium hydroxide required to saponify 1 gram of oil or fat. Saponification value is a measure of the alkali reactive groups in fats and oils and is useful in predicting the type of glycerides in a sample. Glycerides containing short chain fatty acids have higher saponification values than those with longer chain fatty acids. The saponification value along with the iodine value determination have been useful screening tests both for quality control and for characterizing types of fats and oils. The method for estimation of saponification value is about 1.5 to 2 gram of sample is taken in a 250 ml Erlenmeyer flask and alcoholic potassium hydroxide solution is added into the flask. The blank is run without adding the sample. The sample flask and the blank flask is connected to the air condenser and it is kept on a water bath. Cool the flask and the condenser and wash down the inside of the condenser with about 10 ml of hot ethyl alcohol. The titration of potassium hydroxide with 0.5 normal hydrochloric acid is done using about 1 ml of phenolphthalein indicator. Now let us conclude the session. Lipid plays a major role in foods. Analytical techniques followed for estimation of physical and chemical properties is required for making changes in lipid composition. The methods that are used for the analysis of physical properties are melting point, softening point, specific gravity, refractive index, smoke, flash and fire point, turbidity point. Analysis of chemical properties includes Richard-Missel value, Polanski value, iodine value, peroxide value and saponification value. Melting point is determined by open tube capillary slip method, while softening point by closed tube capillary slip method. Melting points of individual fatty acids depends on chain length, number of double bonds and isomeric configuration. Specific gravity is measured using pycnometer and the specific gravity of fats is less than 1. Refractive index varies with temperature and wavelength and is estimated using Bitterer refractometer. The smoke, flash and fire points of a fatty material are standard measure of its thermal stability when heated in contact with air. Oils containing fatty acids of low molecular weight have lower smoke, flash and fire points. Richard-Missel helps to estimate volatile water-soluble fatty acids, while Polanski value estimates the volatile water-insoluble fatty acids. Peroxide value helps in determination of oxidation of lipids. Saponification value and iodine value have been useful screening tests for quality control and for characterizing types of fats and oils. Thank you.